let us continue with sampling. So, S of omega is the impulse train sampled signals spectrum. Two things happen, scaling by 1 over t and periodic repetition with period omega s. And this, if you replace omega by a little omega fs, then you get the DTFT. So, what this step does is it takes the omega s periodic spectrum and you scale it by fs, and scaling by fs converts the omega s periodic spectrum to a 2 pi periodic spectrum, which is what the DTFT is. And that is the connection between the sequence whose values are samples of the underlying continuous time function. The samples are taken cap t apart, but when you plot it as a sequence, you plot them as a sequence of numbers with the independent axis being n, 0 plus or minus 1 plus or minus 2 and so on. And that sequence of numbers has a DTFT x of e to the j omega, which is 2 pi periodic, and that spectrum is intimately associated with the impulse train sampled signals CTFT, which is omega s periodic, by a scale factor of fs, which is the compression of the frequency axis. Compression if fs is greater than 1 and expansion if fs is less than 1. And this is all consistent. Remember, if you are going to scale the frequency axis by fs in the time domain, you will inversely scale. If fs is the scale factor in the frequency domain, 1 over fs will be the scale factor in the time domain. Therefore, this is really t times cap t, and notice that yc of 0 is xc of 0 and yc of 1 is xc of t, yc of minus 1 is xc of minus t. So, this compression by a scale factor of fs in the frequency domain, when I say compression, I am assuming it is the case where fs is greater than 1, which is the typical case that appears in practice. Therefore, this compression by a factor of fs in the time domain leads to an expansion in the time domain, and the expansion in the time domain is such that the expansion factor causes the samples that were originally cap t apart to now be 1 second apart. So, everything falls in place, and this is consistent with the fact that the sequence are placed 1 apart, because the independent axis is n, little n, and the samples are 1 apart, 0 plus or minus 1 plus or minus 2. Hence, you can think of yc of t as doing an expansion in the time domain and then taking samples 1 second apart. If you did that, then your spectrum will be 2 pi periodic. So, all of this is consistent with what we have seen before. And just to complete the picture, so this is already in my notes, I am recapping this point. So, you have a band limited signal xc of t whose spectrum is this, and then when you sample this, you get xs of omega. So, you have a scale factor of 1 over t, and then this periodically repeats. The periodicity is omega s, and now we want the spectrum of the underlying DTFT. So this now is x of e to the j omega. This is also periodic, only that its periodicity is 2 pi. Of course, the way I have drawn this, I have for ease of comparison, I have made this 2 pi line up with omega s. So clearly the second and the third plots are not to the same scale. And the other way of looking at this, rather than looking at the omega scale, you can also look at the f scale, which is nothing but omega by 2 pi, and this point continues to be omega c. So we are compressing by a factor of fs. Therefore, this frequency, which is omega c, now becomes omega c by fs. Note that omega c is 2 pi fc, and hence omega c by fs is 2 pi fc by fs, and this can be written as 2 pi times little fc, where little fc is cap fc by cap fs, and hence if your independent axis is little f rather than little omega, and little f are related by a scale factor of 2 pi, therefore this becomes plus fc. So this is how the analog frequency in hertz is mapped to the digital frequency little f by this normalization, and little f sometimes is also called as the normalized hertz. Therefore, whatever your sampling frequency is, and if you know the true frequency in hertz, if you divide that by the sampling frequency, you will get the normalized frequency. Again, everything is consistent. Omega is dimensionless number because it is the argument to the exponential. Therefore, f also is dimensionless because it is ratio of fc to fs. Fc is in units of hertz, fs is in units of hertz. Therefore, the little f scale is again a dimensionless quantity. And just to illustrate this with a sinusoid, if you had xc of t, which is cos omega naught t, this in turn is cos 2 pi cap f naught t, because cap omega naught is 2 pi times cap f naught, and then if you think of the sequence x of n, which is obtained by taking uniform samples of the underlying continuous time signal. Remember, this x of n is not the impulse train sampling, it is just the sequence of numbers taken cap t apart. Therefore, this is xc of n cap t, and this is nothing but cos 2 pi f naught, replace t little t by n cap t. So, this is this, which in turn is cos 2 pi, cap t after all is 1 over f s, and we know that f naught by f s, cap f naught by cap f s is little f naught, and 2 pi f naught is omega naught, and hence if you have a sinusoid with frequency cap omega naught, and if you sample it at cap t apart, you get a sequence which is cosine omega naught n, little omega naught n, and little omega naught is 2 pi little f naught, and little f naught is cap f naught by cap f s. So, you take the true frequency, normalize it by the sampling frequency to get the normalized frequency, and then 2 pi times the normalized frequency gives you the radian frequency. Now, we will do a few examples in which we are going to take the underlying continuous time signal and then get its continuous time Fourier transform, then we will periodically repeat it and scale it by 1 over t, and then we will replace cap omega by little omega times cap f s. This should give us x of e to the j omega based on whatever we have developed so far, and we will apply this to actual examples and then verify we get what was known to us before. So, as a first example, we will take x c of t to be cos omega naught t. This has continuous time Fourier transform pi times delta omega minus omega naught plus delta omega plus omega naught. This is the continuous time Fourier transform x c of cap omega. Now, we look at x s of omega. You need to do two things: scale it by 1 over t and then periodically repeat it. Therefore, this becomes delta omega minus omega naught plus delta omega plus omega naught. So, this seems identical to the previous step except for the amplitude scale factor. What else needs to be put in here? The so, this is periodic repetition. So, you have to either periodically repeat the impulse or restrict the range. So, this is valid from minus omega s by 2 to plus omega s by 2. So, this is the fundamental copy of the periodic repetition of the spectrum. Now, we are going to take x s of omega and then we will replace cap omega by little omega times f s, and if everything were done right, we should get x of e to the j omega. Let us look at this particular factor pi by t delta omega minus omega naught, that is cap omega minus cap omega naught. We are going to take cap omega and replace cap omega by little omega times f s minus omega naught. We will just concentrate on the first factor and do the simplification. We also know that delta of A t plus b is 1 over mod A delta of t plus b by A. So, now let us apply this formula to this previous term. So, now you have pi over t. So, this is one over f s delta omega minus omega naught by Fs. This in turn becomes pi, denominator is t times Fs, which is 1, and now you have omega minus omega naught after all is 2 pi f naught by Fs. F naught by Fs is little f naught, and 2 pi little f naught is omega naught. Therefore, this simplifies to pi times delta omega minus omega naught, and this should correspond to the samples taken cap t apart. Therefore, this is cos omega naught n times cap t, which in turn is cos omega naught n by Fs, which we just earlier saw. This was nothing but cos omega naught n. Therefore, the samples of the signal taken cap t apart gives us the discrete time sequence cos omega naught n, and the first term turns out to be pi times delta omega minus omega naught. Similarly, the second term will turn out to be pi times delta little omega plus little omega naught, and hence we get the familiar transform pair DTFT pair. Cos omega naught n is nothing but pi times delta omega minus omega naught plus delta omega plus omega naught. Okay. So, what the theory that was worked out for the general case has been illustrated for this specific example. Let us look at a second one. Sin omega c t by pi t is your underlying continuous time signal. This continuous time Fourier transform is the ideal low pass filter with cutoff omega c. So, this is really xc of cap omega. Now, what we are going to do is we are going to sample this. And when we are done with this, we are trying to relate this to this pair sin omega c n by pi n. This is the samples of the continuous time ideal low pass filter's impulse response, and starting from the earlier figure, if everything went right, we should derive this transform pair, and this is between minus little omega c to plus omega c, and omega c is nothing but cap omega c by Fs. And if you replace little t by n cap t, this becomes sin omega c n cap t by pi times n cap t, all right. And now so this is the sequence. The corresponding impulse train sampled signal will be 1 over t, k going from minus infinity to plus infinity, rect of omega minus k omega s, where rect stands for this rectangular function between minus omega c to plus omega c. Okay. So, this is the transform of the impulse train sampled sequence in continuous time. And now, when you all you need to do is you need to scale this by 2 pi to get the 2 pi periodic spectrum, and the samples are omega n cap t by pi times n cap t. K going from minus infinity to plus infinity. So, now this becomes rect of little omega by minus k times 2 pi. So, what I have done in this step is going from here to here, I have scaled by 2 pi, and this should correspond to the discrete time Fourier transform of this sequence, and this sequence is obtained by taking samples of the underlying continuous time function cap t apart at cap t apart, and notice that these two terms get cancelled, and hence you have sine cap t after all is omega c by Fs by pi n. This by definition is now little omega c, and hence this has this. Therefore, sin omega c n by pi n has DTFT, that is periodically repeating with cutoff little omega c. Little omega c is nothing but cap omega c by Fs. So, again this gives us back our familiar transform pair. We know that sin omega c n by pi n is the ideal low pass filter in the discrete time domain. And the final example we will look at is this. So, this is xc of t, and this transform of course is Sinc. So, this is nothing but sin omega 2 by omega by 2. This is not band limited, and hence if you sample this you will get aliasing, and what we are trying to do is we are trying to relate this discrete time sequence between minus cap n to plus cap n. So, this is our discrete time sequence, and we know that this transform is sin 2n plus 1 omega by 2 by sin omega by 2. Therefore, if you take samples of this and then form this sequence, you should get this as the spectrum starting from this. So, what we need to do is the impulse train sampled signal spectrum is x s of cap omega, and that is nothing but 1 over t, k going from minus infinity to plus infinity, and then you need to repeat this sin omega minus k omega s by 2 divided by omega minus k times omega s by 2. So, this is what the sampled signal spectrum is, and x of e to the j omega is scale replacing cap omega by little omega times s. So, this is now 1 over t. So, let me take care of the 1 over t factor slightly differently. So, now I have sine, wherever cap omega is there I am going to replace it by little omega s minus k times omega s by 2, and then I have let me multiply this t here. So, this becomes omega times f s, I will multiply by t minus k times omega s times t by 2. So, now this becomes k going from minus infinity to plus infinity sine. So, f s after all is 1 over t, therefore, this becomes omega times, let me multiply numerator and denominator by cap t. So, this becomes omega times, if you multiply omega s by cap t you will get omega s times cap t is two pi, and f s times cap t is 1. So, this becomes k times 2 pi by 2, and this is the expression for this. So, where this is between minus n to plus n. So, this is exactly this expression, and this expression has been obtained by taking the aperiodic sinc, repeating it periodically with period omega s, scaling it by 1 over cap t, and then scaling the frequency axis by f s. So, these are the steps that were done, and this should really be equal to sine 2n plus 1 omega by 2 by sine omega by 2. So, it does not seem to be like that at first glance, but let us get a feel for what is going on here. The underlying continuous time signal is this, between minus half to plus half, and this is sine omega by 2 by omega by 2, the continuous time Fourier transform, which is aperiodic. Now, what is happening is, when you sample, you will cause periodic repetition of this, and therefore, what is happening here is amplitude scaling by 1 over t is always there. The other thing is periodic repetition. So, this is the fundamental copy, and then you have the repetition on the left hand side. Similarly, you have repetition like this. Remember, each of this is the aperiodic sinc, and this repetition is omega s. Later, this will get mapped to 2 pi when you scale by cap f s. Therefore, this and this are equivalent. So, this is the Dirichlet kernel, which is 2 pi periodic, and you can think of that as taking the underlying analog sinc, namely sine omega by 2 by omega by 2, periodically repeating it and then adding it up. If you add all these copies, you will get the 2 pi periodic Dirichlet kernel. So, that is the connection between the aperiodic Sinc and the Dirichlet kernel. This is nothing but the earliest version of the analog Sinc. So, to really show how this is exactly this mathematically, starting from this to this, probably some other technique is needed. But we know that these two must be the same based on the sampling theorem development. Other thing to note is that in this form you do not see cap n. So, where is cap n being implicitly playing its role here? Yes. So, that is implicitly captured in the parameter t, all right. So, cap n is there implicitly by in the parameter cap t. The other important assumption that is made here going from this to this is that when you take samples, you are taking samples like this. The next sample is here and the next sample is here. That is, after this sample, the next sample falls on this point and similarly on this side it falls on this point. So, clearly the question might arise, right, why not take a point here? And taking a point at the very two ends means that you are sampling at a point of discontinuity, and this development assumes that you are not sampling there. Again, if you remember a statement I had made some time back, you would realize why this is the assumption that is being made. This assumption is needed, that is, you do not sample at the points of discontinuity is needed because you are saying it will be greater than 1. Why is that? Okay. Oh, so you are thinking of Gibbs phenomenon. Okay. So what is the answer? Okay. All right. So you think if I had sampled there, the sample value would be larger. Okay. Your thinking of Gibbs phenomenon is correct, but the fact that the amplitude has to be larger is wrong. At the discontinuity, to what value will the spectrum converge to the average value? Therefore, if you recall, you are not recalling the Gibbs phenomenon exactly. So, this overshoot will be like this. Overshoot will be to the left of the discontinuity and undershoot will be to the right of the discontinuity. So, this 9% overshoot and 9% undershoot will happen to the left and to the right. At the value of the discontinuity, it will exactly go through the average value, and hence if you take samples at the point of discontinuity to be consistent with this development, this sample value has to be, instead of this and this, the sample value that is consistent with this expression on the other side will have to be half. Therefore, in this theory we assume you do not sample at the point of discontinuity. If you want the expressions to match, you have to make sure the sample at the value of discontinuity is really half the value, or rather the average value to the left and to the right of the discontinuity.